Thank you a lot for the opportunity. What I want to do is to show our view from the point of view of a tool called Fab Insights, but also more on the general. So I like a lot of the ideas about digital twin, and one of the things is to basically recognize that it's a there are many problems. At the end of the day, when we are digital twin is more of a solution, but really, what are the problems that we are trying to accomplish or to solve? Well, we want to increase profit margins. We want to create product-specific process recipes. We want to guarantee highest product quality, solve yield problems. When key engineers leave, we don't want to lose that institutional knowledge. And we want to really monitor all the aspects of the fleet, predict future performance for the specific products. So when we are starting thinking about what are all of the things that we need to do, well, we need to start thinking about, well, how are we about to do that? We want to have semantic data in which we are able to integrate all of the data, basically provide meaning. It's not just a set of numbers, but also really incorporate knowledge that exists. We want to make sure that it's an agnostic framework. It needs to fit any computer environment. It cannot be only cloud. There are some requirements for security that some companies prefer to have everything on premise, or even just from the point of view of latency. And at the end of the day, we also need to develop a methodology, because we are not going to be able to say, oh, we are done with the digital twin, that's it. It's more of an evolution process. So we need to have a framework in which we can quickly identify, solve, and prevent future problems. So the way that we think about this is that the digital twin, it's a very, very large problem. So we need to start dissecting it and start building it from the, so have a general idea of what we want to do. But in order to start composing solutions, we need to start composing solutions from the bottom up. So there are three applications that I will be kind of talking about this, which is something to monitor a process, something to monitor tools, something to make forecasts about performance. Why the selection of these units hopefully will be clear. It will be clear more or less at the end of the presentation. So this is a marketing slide, and I promise that I only have like 2 of those. The rest is going to be actually real data. But this is mainly to kind of convey what the digital twin approach from Siemens is, in which we want to basically make a combination of all of these different areas, which is we have a product life cycle, we have a production life cycle, and at some point they intersect with each other. So what the digital twin approach allows us to do is to basically say, well, within the areas that we are doing when we are doing the production, how is this information going to be propagated during the production side? So the way that we are solving this is by the concept of digital threads. So what is a digital thread? The digital thread is the recognition that instead of solving the whole problem and trying to create kind of this hierarchical infrastructure from the top down, is to say, no, we are going to solve individual problems or threads from the bottom up. But as we are doing them, we are going to be doing them in a way that they are compatible with each other, so that it's almost like building Lego bricks. We create different Lego bricks that are going to have different sizes, and then it's a matter of putting all of these different pieces together. So when there is a new requirement, you already have a menu of solutions that you are able to kind of concatenate and put together. So as I said, these are going to be I would say the marketing presentation and on the engineering side. So I like this from the visuals, but at the end of the day, it's easy to do the talking. It's more difficult to actually showcase, well, that sounds like an interesting idea, but where is the meat? So this is another view to look at exactly what I was saying, that if we think about building a digital twin through these threads, we can think of a full system as in this axis having a collection of tools, in this axis having a collection of tech nodes or processes in general. And you can think of a process monitoring instance as something that is looking at a specific tool for a specific process. You can think of cross metrology as something that it's able to concatenate multiple processes together for across multiple tools. And then you can think of tool monitoring as something that is basically monitoring a tool across multiple tech nodes and processes. At the end of the day, really the whole point of having a unified view of all of these different pieces is to say, well, now we can start answering very interesting questions. Instead of, for example, now, if all of these pieces are put together, now we can start asking questions as to, for example, what will be the electrical performance of a specific device when it goes through the specific state of a particular tool? Or what will be a specific yield value when it goes through a selection of multiple processes or multiple tools or multiple process sequence. So by putting all of these different pieces together, you start seeing that as they are getting concatenated, the nodes start to be realized, and then at some point, at any point of that particular matrix that now, or this fabric, this digital fabric that we are creating, through all of the threads, we can start asking questions that perhaps even at some point we didn't know that we had. So now let's actually go with examples. So that's kind of the overview. So the idea is, again, we want to incorporate process and design. We want to, somebody is maybe can go on mute unless there is a question. Is there a question? Okay. So
the prompt?
Can somebody perhaps put the person
that
is talking on mute? I don't think that he's paying attention. Thank you. So what we are going to be trying to do is to look at the characteristics of the design and incorporate that information. So from the point of view of Siemens CDA, we are very proficient in understanding what is the physical verification, optical proximity correction, and so on of specific electronic devices. What we do is that we do a characterization of those specific products, and we collect information that then is going to be propagated forward to the production side. So typically, especially in a fabless foundry environment, it has been, well, there is a physical verification component that basically says this is what is going to be done. There is a guarantee that then is going to be able to be manufactured, but that's about it. That's about the communication that exists between the two pieces. What we are trying to do is to basically say, let's go and actually bring additional information that is related to the design, feed forward to the production side, and then incorporate it and merge it with the process and metrology information. So within this particular block, really the problem that we are trying to solve is, ideally, when you're manufacturing any process, you would like to have maximal characterization of the devices that you are building. We know that in reality, you are not able to do that. You cannot measure every single position on a wafer. So in this case, it will be like sections of a wafer. You cannot measure everywhere on the wafer for every process, for every lot, for every wafer that is being processed across all of the technology nodes. What we want to do is to basically say, well, in order to, if we have a problem and we want to figure out what is the stack of processes that happen in that specific location and the response in that specific location, well, since we cannot get the physical measurement, we can get a virtual measurement. And again, this can be done because if we are able to collect all of the necessary information to merge the process, the metrology, and the design to characterize the full response, we are able to start making some of these predictions. So this is just another way of looking at it. We have the product. There are all of these different product features. So this is exactly the same design, but it gets sampled in a different way, that it is trying to collect the understanding, the physical meaning of what is important during the manufacture of that specific process, that it gets connected to the process and manufacturing information in which the two are combined. And what that allows us to basically just pick any target of interest. We can basically say, okay, so how I want to make an intermediate prediction, how I want to take a look at an optical measurement, a physical measurement, an electrical measurement, a tool performance. Doesn't really matter what the target is. That's the whole point of having a digital twin, that you are able to model what are all of those transformations that you need to do at every step of the way. Let's go through some examples. So, and by the way, if you have any questions, I'm going to try to have time enough to answer them. but it might be much easier if you interrupt me. So again, feel free to do so. Let's start with some of sample results. Virtual process exploration. What does that mean? In this particular graph, we are basically saying, well, we have some sort of target. We have multiple products. This is during the training of the model. So this is experimental. The little square is an experimental value. These are across multiple products. So we know that every product is going to have a slightly different response to the process, so a specific characteristic to the process. But now in this particular case, it was a methyl thickness for the target. So we can see that now we can start making examples that says, well, what would happen if we try to create, so for example, in this case, it's a circle, so that was product one. So we say, well, if we were using the characteristics, the process conditions under which product one was manufactured, how would other products respond? And that's why, this is the different markers. That's how all of the different product responds. In a similar way, when you go to product two, that will be the characteristic that you will have with product two, but you can start making a simulation as to how the different products will behave across different set of process conditions. So what does that mean? It means that different products react to different process conditions. Okay, great. At the end of the day, that's not necessarily what we want. What we want is to have some sort of consistent performance. So now that you have a model that you are able to utilize, even though this is another process, so this is for a dopant concentration, that's the target. So each one of these dots corresponds to a different product. And what this is basically highlighting, this is one of the process parameters that typically gets optimized for individual products. This process is cumbersome because you need to take that particular wafer, you need to make a destructive measurement, figuring out how the dopant concentration looks like, and then come back and try to go and solve it. There are things that can be corrected during the automatic process control. There are other things that are too long in order to close a loop in a reasonable amount of time. Then once you have a model that is able to understand how different products respond to different process conditions, then you can simply simulate and optimize it and come up with what is the optimal set of process conditions in order to have an optimal target. Because at the end of the day, that's what you wanted. That's what your targets are supposed to be.
So
yes.
Sorry, on the go ahead, Conrad.
I have a question. So Andres, obviously you cannot, look at the entire wafer, right? Plus there are variations from wafer to wafer. So are you using some stochastical modeling to figure out what to sample?
No. So that's actually a very good question. I think that I have a slide that talks about that. So actually what it happens is that there are wafer-to-wafer variations, but in many instances, those wafer-to-wafer variations, they can actually be mapped to responses that the design has given the process conditions. So this is why it's super important to have these three components. You need to have the characteristics of the design, characteristics of the process, meaning, for example, what the temperatures, pressures, voltages, flows, and for basically all of that data is actually collected in a per wafer level. The measurements aren't, right? Because the measurements are only maybe one wafer per lot or something along those lines. So not even a position across all of the lots. So what we have found is that once you integrate all of this data, there is actually a lot of information that turns out that it is systematic, that typically has been considered to be stochastic. And we kind of have been considering it to be stochastic because we didn't have a better way to do the characterization. But I think that I have some of the slides that basically show that by doing this particular process of combining everything, it turns out that there are more things that are systematic than what we thought there were.
Okay, thank you.
Yeah, Andres, for this example, did they also collect the experimental data after optimization? And I believe that would be to say that you close the loop and actually have a digital twin.
Not for this particular case. This case, with the customer didn't want to share that particular data. So, typically
that build those optimized designs, I guess. Did they
well, the designs are not optimized. It's the process, right? Because the design, the process is the one that gets adjusted in order to take now the new value. So after that, yes, it gets optimized, and then they have to go and process it. I don't have here. That's what I hear. I say simulated. The experimental actual values that data, we were not given that data back.
The optimization is multiple parameters or just the parameter on the x-axis gets optimized?
There are multiple parameters. And
Okay.
that's why you also see kind of these that it's not perfect. If it was only one parameter, it would be really nice and flat here. But that's why, you know, there are other things that they need to be taken into consideration. So
okay, very good. Thank you.
Other sample results. So again, so far we are kind of going from we are able to predict how different products react across different process conditions. We can see that if we have that particular model, we can actually go and optimize one specific variable. What this particular graph is showing is that typically every process, because it's different, has to be modeled separately. But once you bring the way that the product interacts with the process conditions, the process really is a level of abstraction that is really not physical, because if you are using the same equipment, the same physics to solve the problem, well, you are able to, in principle, incorporate all of that data. So what these different groups are showing, group 1 through 4, these are actually different technology nodes. So this is a single model that is able to predict across 4 technology nodes, and actually, you know, machine learning loves variability. So with the ability to incorporate data that says, I can actually take data from the 44 nanometer mode and combine it with 32 nanometer data and so on. And that actually, instead of degrading the quality of my model, it's able to improve the quality of my model, because it's allowing the machine learning system to actually see how these much larger variations in process conditions operate within the system. So you can start making now a prediction of blind products that, again, they basically are able to span a very large number of process conditions. You can start identifying areas. I was saying that even in some cases, in automatic process control, you are able to you know, make corrections on the fly, and certain parameters, certain process parameters, they can be adjusted by simply having a feedback loop. What we were able to do in order to look, for example, DCVD and electroplating tools, was that under certain conditions, it turns out that the parameters that are being exercised, they are suboptimal. And there are, again, this is a much larger discussion, but basically just the point that we can monitor the tool behavior, and there are ways that actually are able to uncover places where there are suboptimal conditions when you are actually doing this multivariate optimization. Another things that are really important or interesting is that in this particular case, it was a back-end of line process in which there was an e-test that it was done at the end, just a single measurement that it was used for wafer dispositioning. But what it's interesting is that as you are concatenating now these 42 nanometer, so these 242 processes steps, when you are creating the model, it basically indicates what are the processes, and this cartoon is it's a scale, meaning that it basically shows what are the processes in that 42 sequence that provide the most impact to the electrical performance. And depending on how well that model is trained, so of course, if you only are training the model with 6 products, you're going to have a worse error. So this is error in normalized units. This is you know, you have a higher error, you are trained with more products, you have a lower error, you train it with more products, you have a lower error. But the point is that very early in the life of that particular process, you are able to make a very good prediction of the final result if you are really looking at what the main contributors are. So again, all of these pieces, and again, that was only for one particular electrical measurement for this positioning. You can actually go and extract that for all of the electrical tests that are done for wafer sorting. These are basically now single models that are able to start predicting from physical measurements what are the electrical sort values that you are able to have, in which, you know, these curves are simply just showing train, blind, what is the relative important parameter for that particular case. So we know that different electrical tests are going to have a different dependency on the different process steps, right? It's not only that one particular process step is going to be dominating the result, that there are going to be multiple. And this is when the complexity starts to grow. When we're talking only about single targets or single process variables that need to be controlled, more or less is that well understood. When suddenly you have multiple targets that you need to map or match, and optimize concurrently, while at the same time making modifications in your process, that's when really having all of these models starts to help, because otherwise, if you try to ask an engineer to solve some of these problems by themselves, it's too much of a problem. And this is actually one of the cartoons that to the questions that it was asked. This shows the resolution at which some of these physical measurements are taken across multiple lots. So as you can see, it's almost, well, the question is, how can we, with this data that it's sampling different locations on the wafer and not necessarily the whole wafer, how could you possibly use this information in order to start making predictions that, where you may not even have spatial data? And again, there are actually ways in which, if we understand what is the behavior of that particular product and process, and you start understanding the wafer fingerprints, it is possible to start imputing the data in a way that, yes, you will have a larger error that in the prediction that you're going to have, but you can actually measure it. You can actually quantify it. And in many instances, it's actually going to be relatively small. Now, the benefit, and again, since this is intended also for packaging, what I wanted to also highlight is that when we are going through this process, as I said, building a digital twin is not only about having the tools, but having the philosophy of how you dissect the problem and what are the techniques, the numerical techniques that you're going to be using. In this case, all of the technology that it was developed, that it was shown before, it was really for semiconductor manufacturing. That same technology was used for a dicing problem. So dicing has really nothing to do with etch, lithography, deposition. It's basically literally a blade that is going and making cuts on the wafer. And really what we were trying to do in this particular case, it was to find the optimal conditions under which we reduce the amount of chipping, because chipping is going to be a way in which there is going to be a loss on that particular wafer. On those particular devices. So once you're basically utilizing the formulation and the framework, you can actually go and identify that indeed you could, in principle, you can identify what are the conditions under which your chipping is less, what are the conditions under which your chipping is worse. And of course, then you can go and optimize it. In this particular case, it turns out that it will have to lead to a variable speed on your blades as you are doing the different cuts in the vertical and horizontal direction. Typically, again, the process has been you select one particular speed and then you use that for vertical and horizontal chipping. Well, it turns out that those very simple design of experiments that are currently done, there is much more information behind that can actually be used in order to start leading towards things, again, that we didn't know that it was actually needed. So at the end of so all of those has been examples, and at the end of the day, really now this is more of a reflection that, okay, so all of those are examples, all are the Lego blocks. At the end of the day, really, what is the goal? Well, the goal is that this digital twin framework, at the end of the day, this is the way that we have the problems, right? You found a problem in the fab, you need to collect data, you need to develop a solution, you need to deploy that solution, and you need to validate it. I can tell you that this is something that we have done. So these numbers are actually real. When you go and try to do this from the first time, it takes you about 1 to 2 years in order to solve the problems, because you don't have anything. You need to start building all of these different components. When you have a new problem, in this case, we had a new problem in which now a solution was known, in which we could adapt a solution. Now that takes 2 to 12 months in order to do that. When you have now all of the data collection set up, when you have already developed the solution and you can just simply reuse it, all of these problems that are showing up there, that you can solve that in less than 2 months. And you can imagine that as more of that is being put together and everything is automated and more information is available, our goal is to try to, and actually that should be the goal of a digital twin framework, is to have all of these solutions, all of these problems that will take typically, months to solve in less than a day. Why less than a day? Well, it's the day that it will take to basically do all of the necessary connections, train the model, and then start making a prediction. if you notice here, actually, I included some notes about mating for high connects. All of these cannot be done in isolation. So that's what I think that is very important to talk about. How are we going to be able to do this? Siemens by itself cannot do it alone. I don't think that any company can solve all of this by themselves. What is now that infrastructure needed in order to get us to that particular point of let's solve these problems that are present on the fab in less than a day? Well, like I was saying before, we need to have data that has semantics. So we originally developed a JSON format that we were going to be donating in some of the European projects that we are working on. Since then, we have been working with IPC in the CFX format that basically it's an open format, it's readable. The intention of this is that it provides all of the necessary meaning and information about the data that it is being provided so that then any framework that is able to understand that particular data is able to basically utilize it, right? So in the process of developing an open standard, well, we need to define it, we need to test it, we need to update it with real examples. From the point of view of the tools, as I said, it's not done by just out of historical reasons, but rather identify what are these unit operations, these dissections of the types of problems that we are trying to solve. So for example, in the case of, well, if you know the history of a specific wafer, you need to make a prediction. If you know the partial history of different processes, you want to know a value. Or if you want to know future performance and forecast of a specific tool, you need to use kind of this time series. So every one of these aspects, applications, basically they solve a specific class of problems that then when a new problem comes in, we can see, okay, does it map with an existing methodology? If it doesn't, then, well, it's a matter of generating a methodology. If it's able to be mapped to existing numerical methodology, we simply go and reuse that component. It has to be super easy to use, right? At the end of the day, really the complexity, I would argue, is not necessarily in putting together the digital twin, but how to actually utilize it in context. So this is an example of a proposed interface of what we currently have that basically says, well, you need to train a model, retrain a model, select a model, get a certificate for that model, make a prediction, and optimize. That's all that you need. All of the machinery behind the scenes needs to be robust, needs to understand the data. It doesn't really need to say anything else, but it needs to be basically this light, because at the end of the day, really the goal is if you have the digital twin, you want to go and deploy it in other problems that you're finding. And if you have to go and do a science or academic exercise every single time, this is not going to work, right? But if you are able to use these prefabricated pieces that you basically say, well, I have data, and at the end of the day, I want to create a model. I want to continue updating this model, and I want to have some sort of signature that tells me if I'm continue doing things right or wrong. Well, this is the minimum set of applications that you need to have. Again, all of this is not possible by itself. We have 3 European projects. It would be amazing if we have something in the United States. Mating 4, that was a project that was completed. We demonstrated AI in production systems in semiconductor and automotive. High Connects, this is in progress. We're applying these AI lessons for heterogeneous integration in packaging and automotive and drones. And Connected Chips is a new one that was just submitted last week for funding, in which we are going to extend again those lessons for other industries, including in electrical components and packaging. So at the end of the day, this view that we had for the digital twin, that it was really developed for semiconductors, what now we are trying to do is to basically say, well, those exact same lessons, they can actually be provided into the heterogeneous integration of things, right? Because life doesn't stop at the chips. Life continues, and it goes especially with heterogeneous integration, in which all of these multiple chips need to be integrated into novel products. Really, the question is, well, now what is this relevant information that needs to be communicated between the different industries? Because at the end of the day, this is really not the problem, and this is what I want to convey at the end of this. There has been a lot of work, and there are a lot of good ideas as to how we are able to put together the digital twins. But really, the real value and where really the industry is going to get the value from is that when that base is defined and multiple players are contributing in a way that all of these different tools can interoperate with each other, well, now they basically can be put together and now say, well, there are always going to be multiple and conflicting targets, right? If you want to optimize for performance, you may have one path that you need to follow. If you want to optimize for schedule, you may have to have a different path. You want to optimize for cost, well, that is going to be a different path. So the point is that the digital twin, it's only the building block. It's a very difficult building block that needs to be put together, but at the end of the day, it's core technology that then is going to enable the ability for then the systems to really start making much more informed decisions of things that, as one of the people were asking, things that we thought that they were random. It turns out that actually they are more systematic than that what they really are, because at the end of the goal, again, the digital twin is to reduce uncertainty, error, and randomness of the current approaches, and really it's in operation research where all of these different techniques are introduced. That basically digital twin is at the core, right? At the core is that digital twin is not going to solve the queuing problem or help on the decision making or what is the business component, but it will provide the necessary information so all of these intersections are able to make the best decision for the rest, right? And this is something that, again, it's such a bigger problem that, again, I don't believe that a single company is able to be able to do that, and thus why the need of collaboration across the board. So that was my last slide, and if you have any questions, I will be happy to answer them.
Thank you, Andres. Very interesting talk, and I'm sure there will be many questions. Start with Kanat.
So Andres, thank you for the presentation. I have a question. So when you have digital twins for the various components of the line, for example, are there conflicting responses that you get from various parts of the line? One twin may say, okay, you have to optimize this component. The other twin say, no, that's not the culprit, but something else. How do you resolve these conflicts?
Well, that's a great question, and that's where we are on the High Connect project. Is basically we are at this point to try to answer that question. I think that's still an unanswered question. At least let me tell you how we are trying to even figure out how it can be solved. The nice thing about this particular data set is that it is a full characterization from the front end of line to the back end of line for a semiconductor process, right? So that means that at every single process step, we have physical measurements, and we have also the kind of the final result, which is all of the electrical measurements that are used for binning, for electrical binning, right? So to answer your question, basically that is going to be exactly the point. And we see that it is a difficult problem. What this graph here is showing, I'm sorry that I cannot really share what the parameters are, right? But what this basically tells us is that different electrical targets, they are dominated by different process steps. And again, that is something that it's kind of reasonable, right? It's intuitive. The thing is that now by creating these twins, we are able to characterize it, right? So now really the next question is, when we are doing neuron optimization, unlike the other case in which you only have one particular target and you say, well, within my specific domain, I'm going to be doing this optimization. And when the target is to try to get, for example, a concentration of dopant to be constant, we know that it is really not going to have additional effects. The real complicated component comes in when you have multiple and competing targets that they may or may not drive the process in a different way. So how to go and solve that particular problem? I can tell you that we have a PhD student precisely working on that particular case, because I consider it to be a problem that is worth of a PhD process, right? It's even just trying to figure out what are the, and even the thing is, how feasible it is. We know that it is feasible because at the end of the day, we are creating products. The question is, what is the improvement that a digital twin would have in order to do that multi-target, multi-variant co-optimization? That I believe that formalizing that it's something that it's quite important. But again, the nice thing is that first thing is to collect the data. We have the data, again, front end of line, back end of line, electrical binning. I think that we have at least all of the data to basically try to answer that question. I cannot answer it right now.
Okay, so it looks like you have to do a principal component analysis across all the models to find out what are the things that matter, and that is a very NP hard problem from a computational standpoint.
That is one of the cases. However, we have a benefit. We have physics, and we have
Andres, we lost you.
I'm still here. He froze.
Yeah, Andres. Okay.
Hello.
Hello.
Oh.
You reappeared.
My computer just died, so now I'm dialing from my phone. So sorry about that.
That was
Sorry.
fast. Okay.
Fast,
So,
yeah.
so yes, the thing, what I'm trying to say is that the ability to identify, for example, by using some sort of Shapley analysis to identify which are the main contributors to these pieces. Really, the trick here is going to be how orthogonal are the main components, the principal components of the solution that you have, right? So that's kind of the way that we are going to be approaching the problem of not necessarily dealing with, the hundreds and hundreds of process parameters that we know that at some point really are not important. Really, the question is, we know that only a few process steps are the ones that are dominating the final result. If these different process steps, they are orthogonal to each other, then there is a much optimal solution. If it is not, then, as you said, then suddenly starts becoming like an NP hard problem, right? So if we see it like from a combinational point of view, I think that it is hard. I think that because of the nature of the problem, there are a lot of heuristics that we can actually incorporate in order to solve that.
Thank you, Andres.
Victor, this is Brooke. Can I say one thing? Sorry, I can't get my hand thing to raise, so I don't mean to cut in front of people. I think for me, like one of the exciting things about the digital twins, right, is the potential opportunity to optimize for environmental metrics too, right? And I don't want to lose that in these conversations. So I know there's a lot of endpoints that you can use, and you touched on a lot of them, but I think this really presents a great opportunity to try to optimize both performance and environmental metrics and understand then how some of those choices, right, can affect whatever energy consumption, water consumption, chemical consumption. So I hope that as you guys are building these out, you're taking into consideration those metrics too.
Well, that's actually one of my final slides, right? That precisely is the digital twin will actually say, for example, with all of the data that is needed to make the predictions, it needs to know, for example, how much power it is being used, how much consumables are being used, and so on. So the digital twin itself doesn't optimize for it, right? It's at a higher level that basically says, if I want to optimize for environmental impact, I want to minimize the amount of such and such and such. So that's exactly my point that I was trying to do at the end, that the digital twin is only provides the information, how that gets actually then used, and then it's human, right? It's society in a way that defines, well, is cost more important than environment or vice versa, right? So that's something that the digital twin doesn't really have a solution for that, but that's at least it provides a very objective and
right. It's a way to look at it.
Measure it. Yes.
Yeah, a way to look at it all together. Yeah.
So it's question how we use digital twin. So digital twin is a tool, and we can use it for different purposes.
Yeah.
This actually brings us to my question about the philosophy. You mentioned the philosophy. How do we dissect the problem? And my question is, can we create universal digital twin toolkit? What is the level of granularity for digital twins. We can create digital twin for an atom. It would be ridiculous, but we can physical base of that. Or we can build digital twin for the whole factory, black box with parameters and play, right? So what is your vision, Andres, based on your experience, on your knowledge, what it would be? What is the optimal, say, complexity of digital twins and optimal number of digital twin in a toolkit? Kind of.
So I tried to answer that question. I guess I didn't do a good job. So we consider these three applications, what we call TMON, PMON, and cross metrologies. For us, so far, I showed many examples, right? So we have gone through lithography edge, sequences of back end of line, sequences of front end of line, dicing, etc. And in all of those instances, we have not had to develop another component. So meaning, it's one of those cases that it's kind of heuristic, right? Are these a sufficient set of components where it's so far sufficient? Does that mean that we are not going to find something else that perhaps is needed? We do not know, but the flexibility that these systems have shown, they are suggesting that might be at least a good initial minimum set. Because now really the complexity now comes into doing the connections, but the connections now are very easy, right? Because again, if you define what the product information is, but the process information is, the metrology, and then the what your targets are, I think that's what I wanted to share in this audience, that this is at least the way that we see that we can use those being as the minimum elements, and then how do you combine them or connect them together, that's different, right? That's, now the question is, where do you call it a digital twin? We can call the digital twin the individual component. You can call the digital twin the larger ultra system. And that's what also we wanted to have this idea of threads, right? A thread is basically this idea that you go after one specific problem, but as you are building it, you build it in a way, leaving infrastructure behind that when a new problem comes in, you can start reusing all of these different components. Mm-hmm. So I think that's, what I will propose is, from the point of view of data, the partition between product, process, and metrology is extremely important. And from the point of view of then the individual blocks of processing that data, something that focuses in a process, a unit process, and something that focuses on the tool across processes, gives you that orthogonality. Now you can argue, well, the one that also we call CM, cross metrology, that's just simply a concatenation of process units, and that is true. It's just that actually there are other things that then you can start building, right? You can make it much more efficient if you know that you are within a sequence than if you are in a single process, because you see everything at the same time. But again, if we go to the atomic level, I would argue just model the tools across processes, model the process across tools. And when you do that, basically you have all that you need in order to put it together.
Okay, thank you, Andres. Thank you. We'll continue this discussion. I have more questions, but we have also other people line. So Jim Wieser.
Yeah, thank you, Andres. It's very, very interesting and very important work. And I know it's a big problem looking at the process technology. You touched on, looking at heterogeneous integration, packaging, and other things. And then I also want to think about the aspect of how is co-design at the product end, at the front end of this, feed into it. And have you a vision yet? I know there's a lot to do. Is there a vision yet on how to try to encompass digital twin into the whole product development flow, from the standpoint of design and optimization with the data, as well as the heterogeneous integration and how to integrate different chiplets, if you will, or different technologies together?
So the answer is yes. The trick is precisely that component, the component of bringing product information into the process. That actually is the key. because once you do that, you actually are understanding the interplay that product info has within the process. So that allows you the ability to then decide very quickly to say, oh, these are things that actually, if they were changed on the product side, things will be better. But at this point, of course, we cannot change them because the product is fixed. So but the learning, how those interactions during the manufacturing are uncovered, indeed, they become actually kind of really good nuggets of information that can be transported back. Now, you can also think of once the whole flow it is put together, given that now these models are actually relatively lightweight, there is really nothing, but again, this is now, you said, more of a vision or of a dream, right? The idea that actually, as you are doing those simulations, these are machine learning models that allow you very, very quickly to make estimations as to how your different products are going to behave, right? So if you are given access from the manufacturing facilities to those particular models, you can virtually figure out how your device is going to perform. But that creates, that actually has, I would argue, more than technical issues, logistical issues and business issues that somebody higher in the totem pole than I can answer, right? But again, from the point of view of developing the technology that could enable that, I would argue the machine learning systems give you that performance envelope that will allow you to actually make those models usable at design time.
Okay, great. Yeah, I understand it's a big problem, but I like to have the vision. Thank you.
Yeah, thank you,
Hey.
Jim and Henning.
I just wanted to have a time check. I can hold my question if we are out of time and you want to move on to the other agenda.
Go ahead. We can. We have
the time is going to be up. Okay. Anyway, Andres. Okay. Another simple question. Okay. I want to know how you typically handle multiple objectives. So you showed us the example. I mean, the optimizations are all multivariate, right? But we can have multiple objectives. Actually goes also into what Brooke was saying. Back to one of your examples, like if I want to optimize for the accuracy of a deposition and get the correct concentration, that was like one of your examples. One of the parameters may be the deposition rate. If I slow down the process, I may be able to get more accurate, but that will decrease the throughput and therefore increase the cost of my process. So how do we handle multiple objectives? Is there some automation in optimizing for multiple objectives, or do you typically just combine several cost functions, say you add them together into one cost function, maybe with some weighting, or how do you handle these things?
Right now, to be honest, we have not. So we are in the process of doing. So we are optimizing things that are clear, that have a clear code. Like for example, that particular case of concentration. The way that you can actually see that it was that when we were looking at the electrical performance, there was that additional variability that it was really unexplained. That variability went away when you actually then do the process optimization on the other side to make sure that for every product, it's get processed the right way. So then that way, every product now has the right concentrations. That means that additional noise, that it was really random because you selected one specific flow, and at the end of the day, that was really not what it gave you the concentration that you wanted. So what I'm trying to say is that the problems that we have been going after right now are the ones that have a very clear solution, in which, again, the problems are kind of helping each other, right? By making the concentrations more controllable, that actually improves the quality of the targets that you are going to have. And then, again, basically, these are orthogonal things. You can optimize two at the same time, and there are no things that are conflicting. We have not gone after yet to the cases where we have conflicting scenarios. And I think that for that, really is going to be a matter of, of a higher cost function that actually will have to enable the individual users to decide what is really what they want, right? They will have to say, is cost more important than performance? Is time more important than noise or yield? So those are questions that I would argue are very specific to the products that are being generated. Some products that are kind of legacy, you're going for cost, well, they are going to have a very different solution than the ones that are says, it's time to market. I don't care how much it costs because I know that I'm going to make much more money for this. So So I think that all of that really it's at a higher level than what the tools are. But we are building the tools so that at the end of the day, the user can actually at those levels can make those decisions, right? And I think that that should be the way to do it, right? That it's the application, the goal, what then drives the machine learning the optimization.
And I mean that would be the obvious follow-up, like many multiple conflicting objectives can be confusing to humans. Then can you apply
Yes.
AI techniques to help addressing that?
Yes, exactly. Yep.
Okay, thank you.